Okay, this is the homework 20's hints and examples. The hints for problem 3 and 4. Okay, so for both problems, we're going to use this equation right here, which is, remember, the recession velocity is equal to the Hubble constant times the distance. And the Hubble constant for problem 3, when we deal with problem 3, let me get the mouse right here. When we deal with problem 3, we're going to use the Hubble constant as 72 kilometers per second per megaparsec. Recall also that 1 parsec is equal to 3.26 light years. That's a really important conversion to remember. So we take this equation that Hubble discovered, of course, back in the 1920s, and we rearrange the equation and we solve for the distance to some galaxy. So we use, of course, we use the Doppler effect, and we measure the velocity, and the standard, well, I don't know if it's standard, but a very typical value to measure the velocity is in kilometers per second. And notice, conveniently, the Hubble constant is in kilometers per second per megaparsec. So the kilometers per second in the numerator and denominator will cancel, and then you have 1 over megaparsecs, and the megaparsecs come up to the numerator, and so D will be in megaparsecs. And what we're going to want to do is convert megaparsecs to light years. All right, so what I'm going to do now is, this is the hint right here. Okay, so this, what I'm about to circle, this is the hint. Okay, now that didn't really circle very well. Okay, so that's really the thing that I would normally show in class, and I'd also do an example, and I'm about to do that. All right, so this is the example I was talking about. Let's say you used the Doppler effect on some distant galaxy, and you measured the speed of the galaxy to be 12,475 kilometers per second. So the question is, can we find the distance to that galaxy in light years? All right, so we're going to use the equation, the equation that Hubble discovered in the 1920s. So it's the velocity is the distance is equal to the velocity divided by the Hubble constant. All right, and in problem 3 and in this example, I'm going to use the standard Hubble constant nowadays is right around 72 kilometers per second per megaparsec. That's the thing that most people use. All right, so this is pretty straightforward. 12,475, that doesn't look like a 5, 75 kilometers per second divided by 72, right, 72, and it's, of course, kilometers, that's supposed to be a K, kilometers per second per megaparsec, all right, and so when you do that, it's fairly simple and straightforward. The answer you get is 173.3 megaparsecs. All right, and remember, mega is millions of parsecs. All right, so megaparsecs. And what we want to do is, remember that they want to know what it's fine that you get megaparsecs, but we really want, for that to be a more useful answer, we want this to be in light years. All right, so we're going to take the parsecs part of this answer, and we're going to say, well, in 1 parsec, there is, of course, 3.26 light years. All right, and notice the parsecs cancel. And we keep the mega, right? So all we're doing is we're multiplying 173.3 mega times 3.26 light years. And the answer will come out to be mega light years, right? So millions of light years. And so the answer comes out to be, let's see, I just did this, 564.8, and the way that we say this would be mega light years, right? And remember, mega, capital M, always stands for times 10 to the sixth. So, if we were to convert this into an actual number, it would be 564.8 times 10 to the sixth light years. All right, so that's our first example. We're going to I'm going to give the hint for problem number 4 now, and then we'll do an example very similar to problem number 4, which is, as you're going to see, is basically still just using this equation right here. Distance is equal to velocity divided by the Hubble constant. All right, so here's the hint for problem 4. Recall the Doppler formula, which is called, the Doppler shift formula, is that the velocity, here, let me get the cursor here, or the mouse, the velocity is equal to delta lambda, that doesn't really look like a delta, does it? Delta lambda divided by lambda naught, where lambda naught, of course, is the rest, the wavelength when the object is in the lab or at rest with respect to you, times the speed of light. And the typical thing that we do is to use the speed of light in kilometers per second. So 3 times 10 to the fifth kilometers per second is the typical value that we use. Okay, in the problem in the problem that they give us in the textbook, they give us the value of delta lambda over lambda naught, like that. They give us this as some number, some decimal number, and so you multiply that times the speed of light in kilometers per second, and then you plug. Then it's going to be something significantly less than the speed of light. You plug that in, as the velocity, and for some reason, okay, I'm not really sure why. They're not using the modern value of the Hubble constant. They're using an older value, and they tell you in the problem. I don't know. Like I said, I don't know why. Just do what the problem in the textbook is asking you. The problem is they tell you to use the Hubble constant as an older value, 70 kilometers per second per megaparsec. So you use that 70 there as the Hubble constant. Like I said, I don't know. I'm not exactly sure why they wanted to do it that way. All right, so I'm going to do an example very similar to this, and actually going to expand on the example just slightly, and you'll see what I'm talking about. And it's going to be very similar to the problem that's in your textbook. All right, so this is the example that we're going to do for similar to problem 4. Like I said, I'm taking this a slightly more realistic type of problem. Usually in these type of problems, you're given you're given that the value of delta lambda over lambda naught as a percentage. And so what you do here, this here, I didn't actually mean to draw the C here. Here, let me erase that for just a second, and we'll put it in there in just a minute. So normally you're given the speed of light as oops, sorry, you're given this is really called the shift. Delta lambda over lambda naught is called the shift. You're given it as a percentage, and so what we generally do is we convert that, of course, to a number. Oh, come on, why isn't this working? To a number. I don't know why this is not working. All right, let me start this example one more time. Sorry about that. I didn't mean to write the C next to the percentage, although you're going to see that's what we're about to do. Anyhow, you're given delta lambda over lambda naught as usually is as a percentage, and so what they gave us in the problem for problem number 4 is they just gave us the number. So all I've done is I've changed 7.8 percent into an actual number, 0.078, and then what you do is basically this is what the problem is about. We're going to use the Doppler shift formula, right? The distance is equal to the velocity divided by the Hubble constant, and that's the goal. But the thing is, we're not directly given the velocity. We have to calculate the velocity, and so what you do is you multiply, this 7.8% times the speed of light, and so that would be 0.078 times 3 times 10 to the fifth kilometers per second. Okay, so we do that, and we'll get what the velocity is, and I did that, and I got 23,400 kilometers per second. See, that's the only difference between problem 3 and problem 4 is you're not given that recession velocity directly. You have to calculate it, and so that's what we did up here. Okay, we're just calculating the recession velocity, and so and I'm going to use the same numbers that they used for the Hubble constant. In this particular case, I'm going to use 70. Again, that's an older Hubble constant. Nobody uses that very much anymore because it's not accurate. Kilometers per second per megaparsec. And the answer comes out to be, of course, the kilometers per second cancel in the numerator and the denominator, and the megaparsecs come up to the numerator. So it comes out to be 334.3 megaparsecs. All right, now we're going to change that into light years. All right, so I'm going to get a new screen here, and all right, just give me a second. All right, so remember our distance. So the distance was 334.3. Geez, that doesn't look like a 4. I'm sorry. 334.3 megaparsecs. All right, and so that's an M. We do the standard thing. 3.26 light years in one part. Shoot. Hold on. All right, sorry, I incorrectly flipped the parsecs. I put that in the numerator in the last things. I apologize for that. All right, so anyhow, the parsecs has to go in the denominator. Of course, there's 3.26 light years in a parsec. So the parsecs cancel, and that gives us the number of light years, which I get to be 1,089.8 mega. And of course, the mega hasn't gone anywhere, but now it's in light years. All right, so just to let you know, another way of saying this, just in words, right? If you had $1 million and you had $1 million 1,000 times, that would be a billion. So this number right here is 1.085 billion light years. That's just a way of saying that, saying the exact same thing. All right, so 1.089, well, I guess 898 billion light years away. That would be how far away that particular galaxy is. So that's the example. Remember that for the problem number 4 that they give us, you didn't have to change the percentage to to a number. They just give you what the number is. So just multiply that decimal by the speed of light in kilometers per second, and you'll be fine.